Hello guys, welcome to Last Hour Mathematics. Today I'll be teaching you Lamis theorem. It's a continuation of resultant of a force. Now I know some of you will be wondering why I've placed Lamis theorem and the resultant of a force. In fact, the Lamis theorem is a theorem to prove that when three forces are in equilibrium, then when you draw a force diagram for those forces are going to close up in that force diagram. Okay, that's the concept of triangle of vectors or triangle of forces. Okay, so what Lamis theorem wants to say is, if we have three forces and those three forces are in equilibrium, if I try to add those forces using a vector diagram, there will be no resultant because those three forces will close up automatically. If those forces don't close up automatically, then we join a line from the tail of the first one to the head of the last one to get the resultant. But once they close up, there's no line to join those forces, which means that those forces are all in equilibrium. It means there's no resultant force. So when you are given questions which requires Lamis theorem, because the forces in consideration are in equilibrium, there's no way they are going to ask you to find the resultant force because it is known that the resultant force will be zero. So rather, in Lamis theorem, you'll be asked to find an unknown force, not the resultant force. So you have three forces. You'll be told these three forces are in equilibrium. So find the unknown force. You are not being told to add all the forces to find the resultant. So that's what we are about to look at today. So assuming I have three forces in equilibrium, let's say I have a bar here, a rigid bar, which is hinged so it doesn't move, and I have an inextensible string, one here, another one here, holding a body, okay, holding a specific body. Now remember, the body will also have a weight which acts vertically downwards. So this is kind of like a string holding this body. This is the first string, this is the second string. But you see, this is what happens in mechanics. When you distort a string, the string tries to oppose that distortion and restore its dimension. So if you stretch a string this way, okay, what happens? It tries to oppose that force, which is what? Stretching it. So when you stretch it this way, so you can see when this body hangs on this string, it stretches it this way. So the string tries to oppose that force which stretches it. And that's what we mean by tension inside the string. So the tension wouldn't act in the direction where it's being dragged, but it will act in a direction to oppose that distortion being caused to it. So it will act this way, T1 and T2. So these tensions are forces, okay? And this weight is also a force. So this diagram we've drawn here is called a free body diagram. Free body diagram. And we will prove that when you hinge a body with inextensible strings in this manner, the whole system will be in equilibrium because it won't move because you've hinged it here and here. It means triangle of vectors would apply here. Okay? So we want to, for this particular scenario, we know that these three forces will be in equilibrium. So definitely if you draw a force diagram, they'll close up with no resultant. So this is what we are going to get. Let me label here as theta, this side as alpha, and this side as beta. So as I told you, you'll be told to find an unknown force, either T1 or T2 or W. But remember, when you are told to find this, it's likely you know this and this. When you are told to find this, it's likely you know this and this. So there are so many ways the questions could come, but you need to understand the concept. So let's go. So if these forces are in equilibrium, then they must obey triangle of vectors. And remember, triangle of vectors is only for three forces. So this force here has a line of action, okay? Take note if you don't know. It has a line of action. So when the force goes this way, automatically means you could trace this line of action here. Can you see? and this force can be transposed here. Okay, we want to draw a triangle of vectors for this force diagram. So this weight, I can transpose it here and have my weight here. Okay, and I can also transpose, let me push the weight here a bit so it makes it more clearer. So let me push my weight here a bit. So you can see we are developing a force triangle. See, we have one going here. Can you see? Have another one going here. So you can see the force diagram. It follows a specific sense. Now I explained that in my previous video, clarification of parallelogram law of vectors and triangle of vectors or triangle of forces. So you can see it's following the sense, and this means that they are in equilibrium because the force diagram closes up automatically. So now let's find the angles here, here, and here, so we could make meaning out of what we've done. Because if weight is here, what I'm trying to say is that there's weight also here. Okay, if T1 is here and I extend it backwards, it means T1 is here, and this was at T2. So let's try and get the angles so that we can use some principles in triangles to find, let's say, an unknown side or an unknown angle, and this will automatically bring us to the Lamis theorem. So let's see, how do I find the angle here? How do I find the angle here? Let's try and extend this line to make it simpler for us. So if I have theta here, this whole angle here is supposed to be 180, so this side will be 180 minus a theta. Okay, now how do I find the angle here? Now this side is parallel to this side, so remember from angles, this and this are alternating angles. This side and this side are alternating angles. So if here is alpha, remember angle on the straight line, here is 180 minus alpha. So if 180 minus alpha is here, means alternating, we also have 180 minus alpha here. Now how do we find the angle here? Also, let's see what we can do. How do we find the angle here? The angle here alternates here. Can you see? This is parallel, this is going down, parallel line. So the angle here alternates here. And if here is beta, what angle do we have here? Okay, if here is beta, what angle do we have here? Because if we have beta from here to here, automatically here is 180 minus beta. I think the force diagram should have been drawn well. We have the angle coming from here all the way to here. Okay, from here all the way to here. So if this whole side is 180, then here is 180 minus beta, which makes here also 180 minus a beta. So let's draw our force diagram very well so we understand what's happening here. And this can only happen, the force diagram can close up this way for forces. Let me draw it the same way we see it here. So it can happen, this can only happen when we have three forces in equilibrium. Okay, when you don't have forces in equilibrium, they will never close up this way. So I have a T2 here, I have a T1 here, I have a W here. Now all I'm doing is just to let you appreciate the Lamis theorem, but actually what you need is the formula. Okay, so what we have here is 180 minus beta, 180 minus theta, and 180 minus alpha. And remember, in my previous video I spoke about the sine rule. So if we apply the sine rule here, okay, what do we get? This side over the sine of the opposite angle equals this side over the sine of the opposite angle equals this side over the sine of the opposite angle. So what I can say is T2 over the sine of 180 minus alpha equals T1 all over the sine of what? 180 minus beta equals W over the sine of what? 180 minus what? Theta. And this is the sine rule. Okay, this is what we call the sine rule. But because of the nature of the question, such that all the forces are in equilibrium and we have only 3 forces and you can apply this rule, we give it a different name called the Lamis theorem. So this is what the Lamis theorem means. This is a bit complex. Let's break it down a bit. Now, I wouldn't break everything down. I'll only break one side down so you do the other ones. Now, in trigonometry, when you are given a ratio like sine A minus B, okay, it's expressed as sine A cos B minus cos A sine what? B. This is a mean. So when I'm given an expression like sine 180 minus alpha, then I have sine A, which is sine 180 sine alpha minus what? Cos 180 sine what? Alpha. Okay, so what's sine 180 on our calculator? The sine of 180, you're having 0. Sine 180 is 0, which makes everything here 0. Now what is cos 180? Cos 180. Cos 180 is -1. So I have a negative here and a -1 here, the sine of alpha, which gives me positive sine alpha. Which means everything we have here is sine alpha, which means everything will also have a sine beta, and everything we'll have here is what? Sine what? Theta. So the Lamis theorem reduces to T2 on sine 180 minus, no, T2 on sine alpha, equals T1 on sine beta equals W on sine theta. This is the Lamis theorem. Okay, so it's a very simple approach. From the vector diagram, we drew a force diagram. We use the idea of triangle of vectors. We use the idea of sine rule, and we arrived at this formula. So this is what you should know. This is the Lamis theorem. So let's take a look at a question and how we can solve a question using the Lamis theorem. But before we look at the question, let us finally look at how we need to represent our formula. You know that initially we were given the force T1, T2, and W, and we constructed this force diagram to derive our formula. So this is how the question will be given. You wouldn't draw a force diagram closed for you. It wouldn't be closed. Okay, so you'll be given the question this way, and you are supposed to use this formula. Okay, so this is what you are actually going to have. Can you see? You have a force T1 here, T2 here, and W, and you have to use this to solve your question. Okay, so what it means is we have T2 over sine alpha. So this is what it means. You have T2 over the sine of the opposite angle. So you have a force and an opposite angle diverging this way. So we have this force T2, and we have the two other forces, and there's an angle between those two other forces. That's all we have here. I'm trying to make it simpler for you. So when you take T1, look at the two other forces and the angle between them. That's what we have here. When you take W, look at the two other forces and the angle between them. So that's what we have here. So let's look at the question. Now, we've been told here, a body of weight 15 newtons is suspended by means of two lightning extensible strings, which are inclined at 60 degrees and 30 degrees to the downward vertical. Okay, calculate the tensions in the strings. So here we have been told to find T1 and T2, both T1 and T2. And before we proceed, I want you to know that Normally in these questions, you will never be asked to find resultant forces, which I've already said. Resultant force in a question where we have forces in equilibrium, all the sum of the forces is equal to 0. There's no way you have a body here, hinged here and here, with the body moving. Once it settles down, all the forces will cancel each other and they will be in equilibrium. So this is what we are having. It means Lamis theorem can apply here. So let's go. The bodies are inclined at 60 degrees and 30 degrees to the downward vertical. Okay, so we can use respectively here, or once the forces have not been specified, you could put your downward vertical to be here at 60 or here to be at 30. But ideally, we need to specify which one has the 60 and which one has the 30. But it's a principle we are interested in. So this is our vertical, and when we say downward vertical, this is the angle we're referring to. Okay, so the angle here is 60 and the angle here is 30, and the angle here is 90 degrees. You can see it's a right angled, it's forming a right angle geometry here. So if we have 30 here, what do we have here? 60. And if we have 60 here, what do we have here? 30. So this is the force diagram we'll be working with. And look at what we have. It's always the force over the sine of the opposite angle, the force over the sine of the opposite angle, the force over the sine of the opposite angle. So here is very simple. Let's try and find those angles. So let me just draw a reference line, a reference horizontal line here. So if we have 30 here, what do we have here? 30. Can you see? Because they are alternating. When we have 60 here, what do we have here? 60. Now this is angle on a straight line. So we can add this and subtract from 180. So 60 plus 30 is 90. Subtract from 180, what do we get? 90. So we've got the first angle here. Now we need the angle from here all the way to here. And we know from here to here is 60. So this side is 90. So we have 90 plus 60, which gives us 150 degrees. That's from here all the way to here. Now let's find the angle here. This side is 90. So 30 plus 90 gives us what? 120. 120. So we have 120 here. So this is the force diagram we have. T1, W, T2, we have the angle here to be 90, angle here to be 150, and the angle here to be 120. So I need to pair one of these, or pair this, or pair that to find an unknown side. So first, if I want to find T1, okay, T1, I need T1, I need to pair T1 one side of this relation to another side. But remember, we have been given our weight to be 15 newtons. So I can say, okay, T1, can you see? T1 over the sine of the opposite angle, that's sine of 150, equals T2, okay, over the sine of the opposite angle, which is 120, equals W over sine 90. And W is 15, okay? So let's rewrite this as T1 over sine 150 equals T2 over sine 120 equals 15 over sine 90. So we could pair this and this to find T1, and pair this and this to find what? T2. Or after you get T1, you could pair this and this to get T2. Anyways, so let's find it this way. T1 over sine 150 equals 15 over sine 90. So we are pairing the first one and the last one. Okay, we are pairing the first one and the last one. So what is sine 90? So 90 is supposed to give us 1. So 90 is 1. So everything we have here is 1. So this 15 on 1. So I'm having T1 over sine 150 equals what? 15 on 1. So I take my sine 150 here to give me 15 sine 150 as my T1. 15 sine 150 gives me 7.5. Remember, it's a force, so it's in newtons. You could put this T1 here and pair this and this to find your T2, or you could use this and that. Okay, anyways, so let's say in the process of solving your question you made a mistake. Okay, so always solve your questions in such a way that in case you made a mistake, it wouldn't repeat to the next question. So let's maintain T1 and what? The last one. I'm not saying this is a mistake, it's just a guidance. So you can take T2 on sine 120 equals 15 on sine 90. Still maintain the initial question. Okay, so what you have is T2 over sine 120 equals 15 over sine 90. Again, this side is 1, so I'm running out of space, so let's go somewhere here. So I have T2 over sine 120 equals 15. So my T2 equals 15 sine 120. That's when I bring this here. So my T2 equals what? $12.99, approximately 13 newtons. So we have our T2 to be 13, our T1 to be 7.5 newtons, and we are officially done with the questions. We've calculated the tensions in the string. So kindly meet me in my next video and subscribe.